All right, let's dive into something that sounds like it's straight out of a sci-fi movie. What if I told you we could forge one of the world's most advanced materials, not in some sterile, quiet lab, but inside a controlled, high-energy explosion? It sounds wild, I know. Let's find out how it works.
I mean, really, think about that for a second. Can you actually harness the raw power of a detonation to create a material that's just a single atom thick? It seems impossible, totally counterintuitive. But researchers are actually doing it. So let's break down exactly how. So the material at the very heart of this incredible process is graphene. Now, you've probably heard of it. It's been hailed as this revolutionary, game-changing substance for years. But there's always been this one massive problem. Making a lot of high-quality graphene is just incredibly difficult.
To really get what graphene is, just picture a perfect sheet of chicken wire, but make it only one atom thick and built entirely out of carbon. It's this unique honeycomb structure that gives graphene its superpowers. We're talking stronger than steel, more conductive than copper, and almost weightless. It's a true wonder material.
And this brings us right to the core problem, the big wall scientists have been banging their heads against. See, the usual methods for making graphene can be really slow, and they often create tiny mistakes or imperfections in that perfect honeycomb pattern. So a few researchers started asking a pretty radical question. Instead of these gentle, slow processes, what if we just used an immense instantaneous burst of pure energy? Okay, so this is where things get truly wild. We're moving from the what if to the actual recipe. And the secret, it turns out, isn't just about intense heat. It's about delivering that heat with unbelievable speed. The scientific principle behind all this is called rapid Joule heating. Now, the easiest way to think about it is like a controlled, microscopic lightning strike. You take a carbon source, you blast it with a massive pulse of electricity for just a few milliseconds, and that jolt of energy is so intense, it literally forces the atoms to snap into that perfect graphene structure. So it all boils down to this four-step process you see here. First, you get your precursor ready, and this can be something as simple as waste carbon or even biomass. Second, you hit it with that insane energy pulse, either from a detonation or a big electrical discharge. Third, bam! That energy forces the jumbled up carbon atoms to rearrange into perfect graphene. And finally, step 4, you rapidly quench it, cooling it down instantly to lock that new structure in place before it can change back. And when we say intense energy, we really mean it. The process hits temperatures of 3,000 Kelvin in just a fraction of a second. Just to put that into perspective for you, that is hotter than the surface of many stars. It's this extreme, ultra-fast heating that makes the magic happen. And just in case you were wondering, yes, they are often using actual conventional explosives. We're talking materials like TNT or ANFO. These things provide that incredibly rapid release of pressure and heat that's needed to kickstart the whole transformation from simple carbon into high-tech graphene.
But, obviously you can't just set off some TNT in a glass beaker in the lab. This whole process requires some seriously specialized equipment. Think of them as extreme kitchens, designed to contain and control these powerful reactions with incredible precision.
This table here kind of breaks down the main setups. You've got shock tubes, which use explosives to create this focused shock wave. It's like a sledgehammer of pressure and heat. Then you have blast chambers, which are basically these super reinforced steel boxes built to take a beating from repeated explosions. And then there are the Joule reactors, which use massive electrical discharges instead of chemicals, and some of these are now getting to the point where they can produce graphene on a kilogram scale. The key thing to remember here is that this isn't just about brute force, it's about controlled chaos. These chambers are absolutely packed with high-speed sensors measuring every single part of the event, the pressure, the temperature, even how much the steel walls of the chamber stretch. It's all about making sure the conditions are absolutely perfect for creating high-quality graphene. So, after all that fire and fury, what do you actually end up with? What does this explosively forged graphene even look like? And is it any good? Well, it turns out the results are pretty remarkable. What the process creates is a special form called turbostratic graphene. Now, what the heck is that? Well, imagine stacking sheets of paper perfectly on top of each other. That's kind of like normal graphite. With turbostratic graphene, the sheets are slightly rotated, almost like a messy deck of cards. And that messiness is actually a really good thing.
It stops the layers from sticking together in the wrong way, and that leads to a higher quality material with way better electrical performance. And the efficiency? It's just staggering. This process can create materials with an internal surface area of nearly 2,000 square meters per gram. Let me say that again. That means a single gram of this stuff, just a little pinch of black powder, has the same surface area as a tennis court. That is absolutely perfect for things like batteries and supercapacitors. And look, the scientific analysis totally backs up the quality. This quote here mentions things like Raman spectroscopy and I/D/Ig ratios, which, are basically just sophisticated ways of looking at the material's atomic signature. And that signature told the scientists exactly what they wanted to see. They had successfully created extremely thin, high-quality turbostratic graphene with minimal flaws. Bottom line, the explosive recipe works. So here's the key advantage, right? This explosive technique is lightning fast. Think of it like flash freezing food. The speed is so fast that large ice crystals don't have time to form. It's the same idea here. The rapid heating and the instant cooling just don't give large defects time to develop in the graphene structure. And the result is a much cleaner, higher quality product compared to the slower, traditional methods. Okay, so it's a super cool, explosive process that makes really high-quality graphene. But what does this actually mean for the real world? Why should we care about this breakthrough? Well, the potential applications are just huge. The ability to make high-quality graphene quickly and hopefully cheaply has always been the missing piece of the puzzle. This breakthrough could finally unlock its widespread use in things like next-generation batteries, ultra-strong and lightweight materials for cars and planes, super tough protective coatings, and all kinds of advanced electronics. At the end of the day, the biggest takeaway here isn't just about graphene. What this research really is a potential blueprint for a whole new manufacturing philosophy, using these extreme instantaneous bursts of energy to create advanced materials that, up until now, were just too difficult or too expensive to make at any real scale. And that leaves us with a really fascinating final thought. I mean, if we can make graphene with a controlled explosion, what comes next? What other revolutionary, impossible materials are just waiting to be forged in the fire of these extreme, high-speed techniques? The possibilities, it seems, are just beginning to unfold.